Yes.
I don't give permission. I'm gonna leave the meeting. No, I'm just kidding. Okay. If it disconnects, let me know. Okay, so let's say we're trying to, so first question, right? For exam 1, you're trying to predict the ionization energy of beryllium in its ground state, given that the ionization energy of lithium 2 plus in its ground state is 122.45 electron volts. Notice the number of protons and neutrons in the nuclei of both lithium and beryllium make their nuclear masses effectively infinite. Okay. So we're basically asking you to calculate the ionization energy of beryllium 2 plus, beryllium 3 plus, right? Wait. Yeah, based on the ionization energy of lithium 2 plus. And since they both have, beryllium 3 plus has 1 electron and lithium has 1 electron too, you're going to use the hydrogen-like atom energy equation. So let's see. So we're trying to calculate the ionization potential of beryllium 3 plus, and that's equal to what? Oh yeah, that's equal to, in Hartree, it's this 2n, and that's in Hartree's. But I think they want the ionization energy in electron volts. Oh wait. Equal to negative of the energy equation, which is just this. Okay, you with me so far?
Yeah.
So we're trying to calculate that, and they give us the ionization energy for lithium 2 plus, and they say it's 122.45 electron volts. And so based on that, you can, so they want the answer in Hartree's. And if you want an electron volts, it's like z squared over 2n times some constant, so like some c, which would convert it into electron volts. And this just contains all the constants like mass of electron and everything. And we're trying to find that. We know that lithium has, in this case, it has a charge of 3, right? Like, so equal to 3, which is just c over 2n squared. And okay, and that's equal to times some constant, and it's going to equal to z squared. So that's like 3 squared over 2, and it's in this ground state, so it's a 1s electron. So 1 squared times c. So it's like 9 over 2. And we're trying to find this constant so we can plug it into this equation so we could find the ionization potential. And this is going to equal to, if we solve it, it's going to equal to 122.545 electron volts times 2 over 9, which is equal to Cn. And I'm not going to calculate this because I want to calculate towards the end to save like on time, so you can just plug in everything. So for beryllium, it has a charge of 4, so it has 4 squared over 2, and this is a 1s electron, which is 1 squared, and it's going to be times a constant, which is here, and it's going to be 122.45 electron volts times 2 over 9. Now, before I continue, do you confused about anything?
So when you did the first part with the lithium, like a couple lines above what you're doing now, the 3 is because the lithium has 3 electrons and the 4, like the number of Z.
Z is the charge of the nucleus, which is like 3 plus. And that's not the amount of electrons, it's like the number of protons.
So why is Oh wait, no, just kidding. That's the charge. Okay. Okay, yeah, I'm good. Keep going.
Okay, and from here we just solve this, and I got my calculator here. 4 squared by 2 times 122. Oh wait. Divided by 2 times 122.45 times 2 divided by 9 is equal to 217.68 electron volts. And the reason why this makes sense because if you really think about it, this is a higher charge, and it will take much more energy to take out the electron with a higher charge than it is for lithium at a lower charge, and its ionization potential is 122.45 electron volts. So it's just some reasoning right there.
Okay, yeah, that does make sense.
Okay, and I just want to like repeat myself. C is just what converts Hartrees into electron volts. It's basically all those constants, you know, like the charged mass of electron and all that stuff, put into one variable. And when I put it into Hartree so I can just ignore variables and I can convert it into electron volts with that C constant. And that makes sense.
Mhm.
Okay. And if he does ask you a question like that, you could in theory just use let's see. Okay. If he asks you the question in electron volts, just use this equation. Because he didn't this is just an equation using electron volts. You can just use this and don't have to matter about finding that C constant. This is what the C is equal to, and just plug in what Z is and just plug in what N is, and you should be fine. I didn't do it that way because I just wanted you to like understand what he was trying to do here by giving you stuff. But yeah, and since it's asking you for ionization potential, it will be positive 27.11 electron volts. If it was asking you for it would be negative.
So instead of solving like and having C equals like in the question we just did, like 122.45 like times 2/9.
Yeah.
And then like plugging that into like converting it from Hardy. Could you just use that?
Yeah, you could use that. I was just
Okay.
trying to explain why, what he was trying to do by giving you that.
Okay. Makes sense.
Yeah.
Yeah.
The concept we solved for is pretty much just this here.
Okay.
Okay. So what is the ionization energy expressed in atomic units for lithium 2 in a 4py electron state? So the only thing that's different is that it's a 4. Wait.
And then would you just substitute in the 1 for a 4 then? Because it's like instead of 1s, it's 4p.
Yes, exactly.
Okay.
And yeah, that's it. And the P doesn't really matter in this instant. Only the N does, because only depending on N. So it would be 3 squared over 4. Oh wait, 2
Is it
times,
still 2 times 4 and then squared?
yeah. And I'll see too. Which is just,
Hold on, guys. Give me a sec.
okay. times 4 squared. Oh my gosh, 2 squared divided by fast 32. There's 102.45 times 2 divided by 1.
Sorry, guys, I'm back.
Problem.
Had a little pet emergency.
It's fine. We all been there. I mean, I wish I'd been there. Almost let me have doesn't even let me have a dog. But yep, it's 7.65 electron volts. And what you can do too is, since you know that the only thing is changing is n, you can just divide, I think it's divide by 4 squared, and you should be fine. Because the only thing that's different for the original, let's say IP lithium 2 plus 1s, is that this answer is just, I think it has like the end on the bottom, and the n is 1, so you can divide by 4 squared and you should get the same answer.
Oh.
If the n was 2 squared, then you have to divide by, I think, 2 squared again? Yeah, you divide by 2 squared. Because 2 squared times 2 squared equals 4 squared, which is what you want. Make sense?
Yeah, so it would be that's 122.45 divided by 16.
Yes.
Okay.
All
Oh
right.
yeah, that checks out. Perf.
Let me see if I got the right answer. I did not somehow, what did I do wrong? Oh, he put in Hartrees. Okay, never mind. My bad. You could have done the question in Hartrees, which is.
So to do it in, oh, the bottom question.
You just do it without the constants, but you don't have to, it doesn't matter. He's gonna count the same anyway.
Okay. This makes a little more sense to me, considering it's like you just use exactly what you just did
Yeah.
instead of switching up units. That's no thanks.
I think what you can do for this, if he asks you something like this and you want to save on time, put the question in Hartrees and just worry about it towards the end, because he doesn't specifically ask what units you use. So what you can do is you can just do you can just calculate it like this, plug in your values, and you should be fine. Which is I suggest that. And if he gives you like marks you wrong for that, just say, well, you didn't ask me not to put in Hartrees. So that's my tip for you.
Okay, so just keeping it in Hartrees with just not doing like the whole C part and just using that equation, the
Yeah.
Z squared over 2n squared.
If he doesn't explicitly ask what units to use, then just put in Hartrees. That's my advice.
Okay.
Even if he gives you this 122 electron volt thing, it doesn't really matter, you know?
Okay, so that whole part is actually just to convert it, I guess.
Yeah, it's pretty much just to convert it.
Okay.
I use Hartrees because it's just easier, and it's it's just like one calculation, you're done, But let's go on to the next part. Okay.
My cats are very captivated in the moving screen right now.
Like
Slightly annoying.
you said your cat is captivated.
Yeah, cats. I have little kittens.
Oh, cool. My friend's cat's birthday on Saturday. He's like debating on dropping me off at my friend's party.
Yes.
The cat's not gonna understand what's gonna be happening, but it's whatever.
It's fine.
Yeah. Okay. Consider beryllium-2 plus cation, comprising of an atomic nucleus with 4 protons and 2 electrons moving around the nucleus that can be accurately assumed to be infinite mass compared to, okay. Write the expression for the electron Hamiltonian H12 of beryllium-2 plus in atomic units with all kinetic energy and potential energy terms explicitly shown. Okay, so I'm guessing you're familiar with multi-electron systems in Hamiltonian.
Sure.
Okay, let's assume you are. So with this, the Hamiltonian is like so basically with one electron it's easy, you just have to deal with one electron. With 2 electrons it's hard. It's like you have to deal with just 2 coordinate systems with 2 electrons. And you have to deal with the interaction term interacting with each other. So you're gonna have a term that's gonna have electron repulsion or potential. And I think that's the only difference with the Hamiltonian. And there's an equation for that, which I put in my review.
Yeah, I started going through that review. I just didn't get through all of it.
Yeah, it's 2 hours.
Yeah, I was working on Sunday, so
Uh,
I wasn't able to go.
It's cool. I picked Sunday because it was more convenient.
Yeah.
Yeah. I thought the test was on Wednesday. That's why I picked Sunday. I should just pick Wednesday. That's fine. Where is it? I just had it. Okay, I think it's close. Okay. Close, almost there. Perturbation. There we go. This baby will help. Yeah. So you can use your notes in the exam, right?
Yeah.
Study your notes because you're gonna know what to look for. Like, oh, they say multi-electron and stuff, because that definitely helped me with the exam. I only got part of the question right. 'Cause I didn't I only say like maybe like a few, and I missed one thing for the exam one, and the last question I couldn't answer. I got a low grade for it. Okay, where is the detailed solutions? There it is. Okay. So I'll put it in color. All right, so this is a Hamiltonian for multi-electron systems. So in this case, you're dealing with beryllium-2 plus. Beryllium has 4 electrons, so if it has 2 plus, it's gonna have like 2 electrons. And so you're supposed to use this term here to, based on its 2 electrons, to what Hamiltonian it has. So first off, Hamiltonian, the first part is the kinetic energy of electrons. So guessing from it being 2 electrons, how many terms do you think we're going to have for the kinetic energy here?
It's just the first part of that Hamiltonian.
It's gonna be all these terms, but we need to know what the kinetic energy, like how many terms do we have? Because we're gonna have like -1/2, and then we're gonna have like 2 terms of this, so it's gonna be like probably like. So I'll just explain help you with the other parts. So don't worry. So since there's 2 electrons, it's gonna be -1/2. We're gonna have 1 squared -1/2, and then that gradient thing, and then squared. So that's why there's 2 terms, because there's 2 electrons. That makes sense.
Yeah.
So there's 2 terms because we're dealing with kinetic energy, 2 electrons moving, and then we're going to have an attraction to the nucleus. Both of the electrons are going to experience the same pull to the nucleus. So we're going to have 2 terms for that. negative, is it negative? Yeah, negative. So it has a charge of 4, number 4 protons, so it's 4 over R1. So this is the coordinate system. We have to deal with the coordinate system of the first electron. And then we're gonna have minus 4 over R2, which is the coordinate system for the second electron. And I think that's it for that. And then this is the electron interactions. So because the two electrons are going to be interacting with each other, how many interactions do you think we're going to account for with two electrons?
Is it 2?
It's going to be 1 because an electrons are interacting with themselves. They're not interacting again.
Oh, right.
Because there's going to be one term. So like 1 R1 2. And just remember it like this. You can't have it wouldn't make sense to have R1 2 and R2 1.
Because it's just the same thing.
Yeah. So you're gonna have only R1 2. And that helps you out with the term because you only have to list one of these ones. So you're dealing with 3 electrons, you're gonna have 2 interactions, and you're gonna have like R1 2 and R2 3, which are the only interactions. Wait, is it R1 2, R2 3, and then R3 1. Yeah, that's my mistake. So arrange them to where you can have only these 2 numbers, like a unique combination. That makes sense, right?
Yeah. Okay.
Okay. And what's your answer for this? Okay, and it's asking, given the difficulty in solving the Schrodinger's equation, we decided to study electron properties of the beryllium-2 plus by perturbation theory. Identify which change or result of part A would include the reference H12 and which terms you would include in the perturbation. So the perturbation just deals with what's changing, like based on our original Hamiltonian, what's different about this one. And based on this, what do you think is the different one? Like it's only one term.
Wait, say that again?
So perturbation theory has to deal with we're adjusting the system to fit another system. So in this case, because it's a multi-electron, we're using old parts of the one electron system. They're Hamiltonian, and we're also using a new part. Does that make sense?
Yeah. So you're asking which part is the new part or which part is the same?
Yes, and the new part's the perturbation term, the first order. So what do you think is the one new part? It's going to be 1.
Is it the, I guess in this whole second equation, is it like the second term?
It wouldn't be that because this will be because they're both using the Hamiltonian, if that makes sense, the 0 order Hamiltonian. Even though they're 2 different electrons, they're still using the same it's just saying 2 systems are here, if that makes sense. Like 2 systems of the 2 systems that we know. So it wouldn't be that. Does that make sense?
So, yeah. So the part with like the one, like the negative 1/2, like that's just 1.
It'll be I'll just say this is the perturbation. I mean, this is just the 0 order because it's asking 1, 2. And so that's including this and this.
Right.
And this and this. Because if you think about it, if it was 1 electron. If it was 1 electron, then you're experiencing attraction to the nucleus, which are these terms here. And you're also experiencing the electrons are also moving, which are these terms here. Now, what do you think is the first order the perturbation Hamiltonian, which is this, which is the thing that's different.
Well, the 0 order is the thing that you marked before, so the other one had to be first then.
This one, right?
Yeah, the one that you didn't mark.
Yes. So, and that's because in a 1 electron system, you don't deal with another electron, so you don't deal with interactions with each other. So 1, 2. Okay. Propose an approximate zero-order wave function for the ground state of beryllium 2+. This wave function must include both the space and spin part, electrons, and it must have the correct exchange symmetry. So, did he teach you about Slater determinants yet?
Maybe.
Okay,
They
so
don't sound familiar to me, but he could have said something about it.
okay, let me just search up Slater determinants. The equation for it, because I just forgot it. So Slater determinants pretty much just help you make a wave function for like a multi-electron systems. Since okay, let me see. X1, 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 X2, X2. So let's see. 2 electrons, we got beryllium 2+. Zero order plus spin. Let me see how he solves it first. He just writes it. Why does he just write it? Okay. He just writes it. So, okay, I think he based it on your notes. So I'll just show you the answer for this. So right here, he just based this on your notes, but he's pretty much saying, okay, so there's like, okay, oh, I just was at it. Thing I wrote before. Okay, so a wave function for this. So since it's 2 electrons, they're going to both be in the 1s. And in the 1s, the possible wave function, the spatial part can be 1s1 and 1s2. And you have to also check if this wave function fits the I forgot what the operator is called, but it just switches your it switches like the electron 1 to electron 2. So it pretty much does this. So onto the wave function, a spatial wave function, it just does this. It makes it 1s2 and 1s1. Does that make sense? So it just makes it a 2 and just makes it a 1. Okay, and from this, you have to also make a wave function for the spin part, which is, what do they call the spin part again? I forgot what the spin part is called. I think you put it here. Okay, yeah. The spin part is like, it can be either go up or down. So since we don't know which electron can be 1 or 2, like it doesn't like think of it like this. We don't know which electron spinning up and which one's spinning down. So we don't know what one is. We don't know if electron 1 is spinning up. We don't know if electron 2 is spinning up. So we make a wave function that puts in those probabilities. So we'll have like alpha 1 plus beta 2. And then that's the first way the wave function can be like, or it can be like this: alpha 2 plus beta 1. And if we apply the perturbation operator, it's just gonna be, it's gonna switch these. Well, these are just gonna be equal to each other, so it'll be like 2 beta 1. That's gonna be plus alpha 1 beta 2, which is the same as the original wave function. And a zero order wave function just means that the wave function itself is symmetric. I forgot to also state this. So it switches 2 to 1 and 1 to 2, but it's the same wave function. So it's like positive 1, 2. If both of these are symmetric, that means the whole wave function is symmetric. So you can pretty much just say the wave function is equal to, and since you wrote the term before, it's and then the spin part. Now, does that make sense? Do you need any clarification on anything?
Give me a second, let me look through again. So since we don't know, no, that's why they're like the alpha with the 1 and the 2 and the betas with the 1 and 2, because we don't know which one's spinning up and down.
Yeah, that's why we include these two probabilities, like this one and this one.
Okay, and then this is used in the equation that we used in the first part, or is this like a different part of the question?
So the alpha and beta is the spin part of the wave function, which is this here. And this here is the spatial part, which just describes like 1s, 2s, stuff like that. And we can make the wave function like this because the only orientation this can be is like, okay, we don't know which electron can spin up or down, but we know that both in the 1s orbital. So that means that this can be 1s1 and 1s2.
Oh, I see.
Yeah. So that's why if it was like something like, oh, it's in the 2s or one is the 1s orbital, one is the 2s orbital, we don't know their spins, then it would be I think it would be like 1s1, 2s2, then plus 1s1 plus 2s1. Oh, yeah, something like that.
And that's if there were more than just the 2 electrons in the 1s.
If there was one electron in the 1s and there was another electron in the 2s.
Okay,
And that's going to be,
yeah, that makes sense. Yeah.
and that's how you make it. You couldn't use Slater determinants, but I don't want to like confuse you. It's kind of like a long, I mean, not a long thing, it includes matrices. Like, and find the determinant of that. But the next part is asking, oh wait, and symmetry just means that if you apply this operator and the wave function stays the same, it's symmetric. If you apply the operator and it turns negative, then it's anti-symmetric. And anti-symmetric wave function times a symmetric wave function will make it anti-symmetric, and anti-symmetric times anti-symmetric will be symmetric. It's kind of like, think of anti-symmetric as negative, I think it's symmetric as positive.
Okay, and that's with which variable?
Symmetric is positive, anti-symmetric.
No, like in the equation, like is it the sigma, or like which part of that has to be positive or negative?
It's so this is the spatial wave function. You're
Okay,
testing out the symmetry for this, and then this spin part, the spin wave function, we're testing out its symmetry, and we find out that we're just testing out the symmetry for both of them, and then we're going to multiply their symmetry together, and positive times positive is positive, and that's symmetric.
gotcha. Okay, now that makes sense.
Okay. Let's see. Let's go part C. Oh wait, we did part C. Part D is pretty much like part C, but except we're gonna do like what's it really? So the zero order wave function, we're talking zero order wave function. The wave function has to be symmetric. When we're talking about a wave function, it has to be it has to be symmetric. Then I mean, when you talk about zero order wave function, that's not like a proposal. Okay, it's wants the wave function. So one part is symmetric while the other is anti-symmetric. So let me just copy this. I'll tell you what it is. And I am unfortunately. Let me see what I did for this one. Just give me 1 second. Let me also check what you, okay, yeah, forgot the radical. All right. Okay, propose a zero order wave function for beryllium 2 plus. Specifically consider an excited state, which space part of the wave function is symmetric and the spin part is anti-symmetric under exchange of respectively the spatial and spin coordinates of electron. Okay, so it's pretty much saying, okay, so the wave function, okay, the space part of the wave function is symmetric and the spin part is anti-symmetric. So what should the whole wave function be because of that?
Anti-symmetric.
Yes, exactly. And so we want the so we need this wave function, the spatial part to be symmetric, and we want the spin part to be anti-symmetric. And I almost forgot. I forgot to put this. It's for it to be normalized. It's just
Is that just specific for this question, or is that for like basically every wave function? Do you have to put the one over red too?
it's for every wave function. I mean, it's for this wave function in particular. If it's a linear combination of like two terms. If it was just like one term, it wouldn't be that.
Gotcha.
Let me double check what I got for the other one. Yes, I got that. All right. All right. So we want, why did I just write that? Okay. So we want so let's start with this. So it's like an excited state. So instead of it being in the 1s, you have a 2s2. So it has one electron here and one electron here. I'm not saying it's actually, it can be up or down. Since we want the wave function to be anti-symmetric, their spins must be opposite of each other. So it can be, this can be going down, this can be going down, but the other one must be up. And if this is down, then this must be up. Does that make sense?
Yeah.
Okay, so we can pretty much use the same. So we'll start with the spin part, which is written like this. So we're talking about two orientations of spin. So it can be if alpha 1 is up, then the other one must be what?
Down.
Yeah, so down goes to beta. Let's say so alpha is up and beta is down. And oh wait, this is 2. And then we're going to go with the other combination, which is alpha 2 and beta 1. Okay, so the middle part is what we need to do. So we want this to be anti-symmetric. So what do you think we're going to add in the middle to make it anti-symmetric?
Minus sign. It has to be negative.
Yeah, minus. We do minus because when we apply the operator, this changes it to negative. So if we were to apply the operator onto this, I won't show the result, but you'll just get the idea this will be a negative after you apply the change in space operator. Does that make sense?
Yeah.
If we wanted it to be symmetric, we would want this to be positive. Yeah. Okay. What else? Okay, and we want the spin part, and we want the spin part to be symmetric. So let me just see spin. All right. Now
Wait, the space is symmetric or the spin is symmetric?
oh, space. I mean space. This is the space.
Okay.
This other one's the spin part. Now, what do you
Okay.
think would be the wave function for this? Think
So
of
the
it.
wave function for that
Think of
is
two combinations. Two combinations of what it can be.
it 1s1 and 1s2?
Yeah, but we're gonna need another term.
Oh,
Think of it. It's gonna be the other probability of it being something else.
yeah, I don't know.
Okay, it's gonna be 1s2 and 2s1. And you know what it is?
Is it because they, well, no, I don't.
It's because we want to include the other way that it can be. So if it can be, we don't know what electron 1 can be, and we don't know what electron 1 is. Electron 1 can be in the 2s orbital, or it can be in the 1s orbital. So we have to include that probability of it being in it, which is the other term here. That's why we include other terms. The reason why we only included just one term here is because they're both in the same orbital. So we can only write this once.
Oh, I see. And now they're in both the 1s and a 2s, and that's why there's another term.
Yes.
Gotcha. Okay.
I think if you just remember that, like just put that in like a note or something, then you should be fine. If it's a situation like 3s or something like that.
2 terms because 2 orbitals.
Yes.
Okay.
And it's gonna be a plus because it's symmetric. And
Yep.
if you apply to operator, yeah, you'll find that to be true. You don't have to apply to operator to show this is right, but it's just to help you like just help explain why that is. And if they said the all right, another question. If they tell you that the spatial part is what damn it was it? The spatial part was symmetric. Actually, wait, let me just like not ask that. Because yeah, let me just not ask that. All right. Yeah, so that will be in your full wave function will just be a multiplication of these two. So it would be alpha times the spatial part. And you can just write that because you stated what those are on top.
You don't have to write the whole thing out.
Yeah, you don't have to write the whole thing out because like as long as you like put in what these two are, you should be fine.
Okay.
If you feeling really confident, you can just write the whole thing and then just like to start from this and then just write the whole thing this times this.
Uh-huh.
Leave it like that, but it just helps you visualize it when you write the drop in the orbitals and then you just like, okay, I do this. When I apply to operator, this happens and stuff like that.
Gotcha.
Yeah, that's what I don't like about Ranieri's notes. Ranieri just like he just writes the answer, that's it, and he doesn't like get an explanation. So that's why so much people didn't do good on this question, because I mean not because of his note, but just because it was just you have to read the notes and you have to like just like, oh, from the notes I see this is it, and so I just do this. So yeah. All right. But then I'm gonna try to go over like one question and I'm gonna call it.
Yeah, I mean, you guys don't have to stay either. I still have to finish your review, but I figured I would come in and ask or seek a live advice.
All right. Advice would
Are
be
you guys doing it
What?
hours tomorrow too?
Yes,
Oh, James back. James,
I've been here.
why were you quiet?
There's nothing for me to say.
Dude, you're smart.
No.
Stop.
I'll let you give some advice, James.
What?
Say your advice.
Say my advice. You have access to your computer.
Yeah.
Wait,
Wait, like
is that
during
home?
the test?
Yeah, I've been told you have like access to your notes.
Well, I like used my iPad last time. It was just like my notes were shitty. Clearly.
Okay, well, here's the thing. Okay, so he likes to use problems similar to what you have done. So if you like, I forget, does he have like those long string of notes where he has like various problems sprinkled out?
Like
Ye-
just practice problems or the ones from the workshops?
Practice problems?
Possibly.
Why don't I think you should try the quiz?
The quizzes also help.
Yeah, I think when I looked at the quiz questions, they look like they can be on the exam, just but from how they're like worded and stuff.
All right.
Yeah, and my review, don't use my review as like 100% fact.
Yeah, I know. It's easier for me to learn through like I don't want to say like this coming out wrong, but like younger people. Because I don't know, like coming to office hours is so much more beneficial to me than like actually being in class.
Yeah.
But yeah.
Say go to class, even though it's like a waste of time. Just like I would say what I did as I read my notes and I went to class. I mean, be honest, I only went to like 40 to 30% of the classes, but I watched all the lectures. But since you don't have recorded lectures, like
Yeah, that's the tough part.
yeah, definitely go.
My battle half the time is like it's not getting out of bed, it's actually just leaving because That's like my only class on Monday and Wednesday. And to come to school for like a 50-minute class just like drains me and my gas tank. So,
Yeah, especially with these gas prices, I understand.
oh my God. I paid $70 today, didn't even fill up my tank.
I've had to pay $80 because I've had to use the highest
Premium?
gas. Yeah,
Yeah,
premium.
me too.
I put in regular once and my whole car like got fucked up.
Yeah, did it like shake and shit? Like you can't even drive it.
Yeah, that's so weird. It's not like it's because it's so used to the premium, I think, and then that's why it does that. Well, you
What
can't.
kind of car do you drive?
I like a 2016 Maxima.
All right.
But yeah, I understand.
Yeah, it's quite pricey.
Yeah, unless you have like your friend just to have like just turn their like iPad, like around, record, FaceTime, watch.
Yeah. I know I do text my group a lot though. They're very helpful.
Yeah.
I'm just like a little slow in this class. Actually, I'm very slow in this class.
Don't worry. A lot of people are.
Listen, I literally just need to pass and get this class over with. Like, I got a job secured. I'm literally starting on Monday. I'm so excited.
What do you work at?
I'm gonna be working at a small startup for like
I am not
beauty and
recording
skincare
anymore.
formulation.